You should be seeing just my slides. And let me just put the Zoom window on the other screen again. There you go. So yes, I will be talking about the value of noise. And what we mean by noise is that when you classically fit a model, you fit to the center of the time series or what have you. And then there's the residuals from your model. And these are generally just used to judge the quality of a fit, but then not really further used. But there is actually information contained within these residuals. So here I'm going to talk about how to make use of this information. And I did this work in the context of a marine ecosystem, so the North Sea, and therein especially the stocks of plaice and sole, two pelagic fish stocks. And these ecosystems, our knowledge of them is fraught with a large degree of uncertainty. There's stochastic growth shocks. So if you look at the time series of these stocks, they vary widely in addition to more long-term trends. And there's also parametric uncertainty. So if you estimate these stocks due to the shortness of the time series that are available, you get quite large error bars. And if this uncertainty is ignored, this may lead to unsustainable harvesting levels. So you might prescribe a harvesting level that for the center estimate should be sustainable, but if you take the error bars into account, actually it turns out a large proportion of the probability weight of this distribution of possible realities is actually not sustainable. And on the other hand, if you properly account for all the uncertainty, you might end up in something like Weizmann's dismal theorem for a climate policy, that you actually need a very strict policy to avoid the collapse of the stocks with 100% certainty. So additional information from early warning signals, they may alleviate this latter issue. So if you then have a more precise estimate about the properties of a system, you can more finely tune your policy to the system and might not need to be as strict. So what do I mean when I talk about early warning signals? So I mean those based on critical slowing down of systems. So this requires a system that has a bifurcation similar to the ones that we already heard about in the keynote this morning. So a proper tipping point in model parameters. And then if you take a time series of a system that has this property and the system is slowly forced towards the bifurcation, the autoregressive property of the time series of that system will tend towards 1 by definition. And so here's 2 examples. One is for an intermediate complexity climate model run of a thermohaline circulation overturning. And if this is forced into up to the tipping point where it collapses, the AR1 indicator tends towards 1. And on the other hand, we have the end of the Younger Dryas. So this is observational data or reconstructed observational data. And there too, we can see in the bottom part of the figure how this indicator tends upwards ahead of the collapse. However, there's one big caveat. To get these nice figures that show a significant trend, you need a huge amount of data, and the forcing needs to move slowly towards the tipping point. Otherwise, you might be tipped before you actually see a reaction in the indicator. So instead of using the indicator itself, we use the likelihood function of the indicator. And thereby we can make use even of very short time series. And I will explain how we do that later. And we don't just apply this to one shot experiment, but we want to actually make a statistically significant claim about the value of using this noise. So we designed a statistical experiment where we generate surrogate data based on a calibrated model of these stocks, generate 25 new observations. So this is a fairly short time window. And based on this, we calibrate the model classically, and then we update it with the information from the likelihood function. And then the value of learning from this noise component, we measure by the slimming of the parameter distributions of the model, so how more precise the estimates get, and the induced changes in harvesting quotas based on a precautionary harvesting rule that I will explain. So this slide has a lot of content, so I'll go by it step by step. In this figure, we see the stock growth response of the calibrated model, and we have a center estimated in the center estimate in the fat line here. So for large stocks, we get a large growth response, and then as stocks get ever more large of a growth response from one period to the next becomes smaller. So the idea is here that we reach a carrying capacity at some point. Then we have this fan curve around it, and that's each of the model parameters I sampled 60 times, the distribution of the model parameter, and then 60 times 60 gives me 3,600 possible states of the world, where each has the same probability of being the correct estimate of this model. And now if I introduce harvesting, we get intersections here between the growth line and the harvest line, and then the intersections, these are the steady states. So this is similar to the population behavior figure we saw earlier, where we also had like these two steady states, defect or not defect. And here I have two steady states. I have one steady state, an interior steady state with a positive stock, a large positive stock that is stable. And I have here an unstable steady state. So if we are to the right of this unstable steady state, we will grow into the internal steady state. And if we are to the left, the system will collapse towards the zero. And then if we look at the system dynamics of this, we can also construct the potential. And the potential is useful to illustrate the escape time. That is one of the crucial things that I also want to talk about in this talk. So if we imagine the system as a ball in this throw, and it is constantly shocked left and right by the random shocks that happen in the system, then we can ask the question, well, how long do we have to wait on average until the random shocks will drive the system over this hump and then into the unwanted steady state at the collapsed stock? And then, of course, intuitively, this depends on the distance between the steady states, but also on the incline here, the amount of height in the potential that has to be surmounted by the system. And so with this type of harvesting rate for the center estimate, we would have a very long expected duration, so 10 to the power of 8 years. So we can consider it very stable. But at the same time, because of a parametric uncertainty, there is already 10% of above 10% of cases that have expected escape time below 100 years. And then if we looked only at the AR coefficient of so the early warning indicator I mentioned of this stable steady state for the center estimate would be a 0.91, which is actually one of the issues when interpreting this coefficient, because the relationship between distance to the bifurcation and this coefficient is not linear. So now if I increase harvesting level, this coefficient increases, but slowly so far. The escape time shortens, and the number of cases that have a short escape time also increases. If I increase harvesting further, now suddenly the coefficient is almost 1, indicating that we are very close to bifurcation, which we can also see here. The potential is almost completely flat. There's not much keeping the state in the system in the stable state. And we also see here that, like, if we increase the harvesting level higher, we will be higher than the growth in the center estimate. And if I increase it further in the center estimate, we have violated the system, but actually there's still 45% of cases where we would say where we would still expect stability, where we would still expect escape time greater than 100 years. So 1 minus this value, right? So in that case, for a policymaker now, it really becomes crucial to have a preference for this risk. So as was discussed earlier already, and if I don't have a proper preference for this risk, implicitly, I will be using the center estimate, and implicitly, I have a preference for a 50% probability of having a short escape time. So what does this learning step now get us? We get smaller confidence intervals for the model parameters. So we have two model parameters, alpha and beta. And as I have 60,000 runs of this experiment, it's quite difficult to show the results properly. So what I did for each of the experiment, I calculate the confidence intervals on the parameters, and then I compare how the width of these confidence intervals changes in all of the individual trials. And then here's the summary. So the 50% confidence intervals in each of the trials shrunk on average by roughly 20%. So this indicates that the center part of the distribution of a parameter actually slimmed down quite significantly. While if we look at the 99% confidence intervals, while they also in mean and in median slimmed, it was not quite as extreme. And then the actual, to get to the actual response of the quota. First, I need to explain the quota that we applied. So we have a precautionary quota. The aim is to prevent an ecosystem collapse. However, we can't have this perfect security, so we allow, I will speed up now because my time is up, 2 parameters. One is what do you define as a short escape time, and then what probability do you allow the short escape time? How likely do you allow the short escape time to be? So I chose 100 years and 5%. And then I got, with the additional information from the noise component, I could again increase my quota a bit and get closer to this true value that I know ex ante from the construction of the model. In conclusion, we can use the critical slowing down for short time series. So this is actually quite nice result. So far, this has not been possible because we don't try to find a trend. And so even if the forcing is moving quicker, we can at least derive some information from this. And the other important thing is that expected escape time is a really useful metric to translate from the uncertainty in many model variables down to a single metric that you can specify in a policy relevant manner with 2 numbers, like how long do you want the system to remain stable and how probable can it be that it is not. So with that, I thank you for your attention and look forward to questions.